All right, so just gonna take a look at this dealer that was talked about a lot recently, Cthulhu. It's been around for a bit. It's very similar to other Steelers like Atomic Steeler, but what's most interesting, at least to me, just looking at this from a reverse engineering perspective, is that it's written in Go, and it allows us to take a moment and have some fun looking at Go binaries. So there's a write up that came out a couple days ago. It mentions Go being the language, and it does what you would expect. Password prompt with OSA script. It actually has a second prompt, which is interesting. Creates a file or a directory inside of this user shared, which has been seen by other Steelers. Yeah, so they cover this, but just want to take a look at this from a disassembly perspective and really look at Go because it's kind of interesting to reverse engineer. So first thing that has caught me off guard in the past looking at Go binaries is main is not what you would expect main to look like. This is covered in other blog posts and stuff, but essentially you would expect, main to have all the main stuff for your function that you're going to be looking at. And that's not how this works. You actually have to look at, I believe it's like a member of main. So if you just type in main like I did here, you can look for like the dot main function for main, and that will give you like information like the actual main that we're going to be looking at here. So if we go there, some of this is going to look really ugly, to be honest. So first thing we see and that we're going to notice as we look at a Go binary is that strings are not null terminated. So this kind of makes disassemblers struggle a little bit with seeing like where strings start and end and all that stuff. So unfortunately, you'll see huge blobs of this type of stuff. So look at this. And it just keeps going. And it's not pretty. But luckily, if we just take a look at what Go strings are, we'll see that there are structs that have two members, right? The elements, which is like the bytes themselves, and then a length, so the number of bytes for that string. So we can use this to actually like figure out what the strings are that are being used in different functions, different calls. The good thing is that this information is much easier to see from a disassembly perspective. So taking a look at this in ARM, we're going to start here. This is kind of weird. And the reason that we're going to start here is because it allows us to talk about page loading and offsets to the page to get the string value at that offset and then get the length of that to see what the string is. So that's a couple things that will be fun to look at. So first, there's this address here, this symbol, go string dot. So if you look at this, it's just like a huge blob of stuff. Not very useful for what we're looking at. But if we look at this from a disassembly perspective, you can also get a hint of it here. This is getting the address of this and the offset of 0x1a from the start of this symbol here. So let's just take a look at that from the actual assembly because it's a lot easier to see. So let's start where first the first time that this S14 is mentioned. So S14 here, the string is mentioned all the way up here. And the reason we're going to focus on that string or this variable is because if we go all the way to the right here, we'll see that it's used inside of this call to this OS exec. So basically like a popen, essentially. It's like a wrapper to spawn a process. So if we go and focus on that first, we'll see the first time it's used is here. And what this is doing, we're just going to kind of comment this out a little bit, is so this is calculating plus 0x8d0 to the address that the stack pointer is pointing to. Right, so this is getting essentially a buffer. So buffer. And then what it's doing, since it's loaded in this pointer to this space on the stack, it's then doing an STP to store two 64-bit registers or zeros. So it's just adding zeros to the address that x27 is pointing to, which is that address on the stack. So it's just putting zeros at that address, 16 bytes of zeros. Next, so the same thing happens. We got to see what the offset of these two, I believe it's 16 or 0x10. Yeah, 0x10. So next, it does the same thing, but this time it's a different offset that it gets from the stack pointer. And then it puts that secondary buffer into x27, and the same thing happens again. So it's just zeroing out those that location on the stack. Okay. After that, x4, there's an OR instruction for x4 for the value of 2. So if you're ORing 0 with 0x2, it's going to be 2. 2 gets stored into x4. And this is a hint as to what we're going to be looking at, since these Go strings are, they are structs, and one of the members is the length. This will end up being our string length. So let's just put a note of that, string length here. Okay. Now we have this ADRP instruction, and a couple things happen here with the X5 register. And this is where we see that call, or like the loading of this Go string with this offset. Luckily, looking at this assembly here, we can see exactly what offset is being added to this page. So we have this page, and we can look at this in Binary Ninja a lot easier. So bv.read, it's all the way at the bottom here. And then we have that address. And then we're adding the 33A. And since we know that this is going to be the second part of this Go string, we know the length is going to be 2 bytes. So we can put 2 bytes here. And then we see that this is for -e, which will be an argument to an OSA script that we'll see as well. Okay, so now let's just take a look at that really quickly. I drew this up to kind of help see it. So when we do this ADRP instruction, this is getting a page, and it's loading that into X5. This page is going to end in 000. That is the conversion of 4K page in hex. So you're going to see these as 000. It gets that pointer to that location. Then it adds the hex 0x33A to this address, this pointer that it now has in X5, and then it saves that into X5. So X5 after this is going to be this, which we use in this bv.read call down here using Python and Binary Ninja. And then this is an str instruction to store this onto the stack at the offset of what the stack pointer is pointing to plus 0x8d0. So that gets put onto the stack. Cool. So let's see what else is put here. So this is most likely one of the arguments that are going to be passed into this. This was the OS exec command. Okay, so then the next thing that we're going to see is we're going to start here. So we know just from my understanding already of Go strings are structs. It has 2 members, the length, and then this pointer to the actual bytes. So we have this F5, which is a huge string length. It's 245 bytes. And then we're having the same thing happen here, where we're getting that address, that page that's going to end in 000, and then we are adding this 0x24A to that address, and that's this here, and then we're storing that at this address on the stack. Okay, so let's take a look at what that is. We can actually copy this instead. So bb.read and then 0x, and this is huge, so it's F5. And that looks like what we've seen in the past with these stealers. This is going to be, I'm just going to put this here as a comment. That's going to be that part of this argument for OSA script that's used. Okay, so next, that gets stored onto the stack like we talked about. So that's there. And now we're getting another, we're going to do another load of ADRP for this page and then get an offset of that. And then we have the length after, right? So we've looked at this before with these Go strings, which are structs. So we can continue that same thing that we're doing. Is we get this. So let's bb.read. Right, so this allows us to read bytes at a certain address. We pass it the address that we want. We're going to add this offset. So you can just add it here if you want to. 3A. And then it is of size 0x9. And that is OSA script. So you can see that here when it was getting this address, but unfortunately, just because of the lack of zero termination, we see that it just sees this huge blob of string data, when in fact it's just getting pointer to that address, which then ends up being this OSA script. So OSA script is then used here, and then this will end up building out the, oh, not that, this copy, and then let's just put this here. So that's going to be OSA script -e, and then it's going to run this huge command. So that's going to be the first prompt that the user will see, which was talked about in this article, this one. Okay, cool. So now let's see other things that this does that are interesting. So there's another display dialog here that we can see that's being passed into this runtime.concat string function, which concatenates 3 strings. So as you can see, it's concat string 3, and we can take a look at that as well. So concat string 3 is going to take 3 different strings. We have this being passed in, and so that's that same thing. So we're loading up that page, adding the offset, and then getting the size. So that's going to be, just to kind of show this, bb.read. And then you can start kind of putting this together in a better way. And then this is going to be, it looks like the address. Yeah. So this will end up being one of the strings that are going to be used to concat and put all these together. The next argument here, we have x2 and x3, which we don't see here. No, x3 and x4. So that's going to be one of the strings that's also used here. But then we have this x5 and x6 registers that are then doing the same exact thing. So this becomes a lot. Once you see one, then it's easier to kind of piece this together. So bb.read and then 0x. Oh no, that's not what I want. So b fd2, and then that is 0x4a in length. Okay. And this is going to be the second part of, well, this is going to be one of the 3 strings that are put together. And we can see we have the title wallet connect. We have this icon, this POSIX file that they use for the icon. And then we see the dialog being macOS wants to access the MetaMask, which is interesting in how that's said. And then we can see that here. So the wallet connect, macOS wants blah 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 blah, all the stuff. Cool. So those are a couple things with Go strings, which can be interesting to look at. And there's a lot of stuff in here that can spend some more time on. So, for example, let's see something that looks interesting. I saw like something BattleNet related or something. Oh, BattleNet checker. So let's take a look at that. If we look at this from this, we see these huge, again, these same strings that are super long. But now that we know how we can work with them, we can figure out exactly what's used where. As you can see, since there's no zero termination, this just continues. And it looks like there's also an mk make dir all, or this was talked about in the report, user shared NW. So then we can also see how that's used here as well. So let's look at that really quickly. So this library application support battle.net, and then inside of x3 that gets stored here is 0x26, and then x3 is used again and then stored. I think that's 8 bytes away from each other. So then that would end up being part of that Golang string. So let's take a look at that as the last one here. So we want to see what the string is. Just clear this out to make this. Use bb.read, and then we're going to put this address. We're going to add the offset the same way that the actual disassembly does. And then this is going to be of length 0x26. And this shows you the actual same register being used. And then since we're saving this on the stack, it doesn't matter that the same register is used for both of these values because it's getting put on the stack 8 bytes away from each other. And then that's going to be the actual Go string. So yeah, so then that looks like library application support, battle.net. And I assume that they are going to get the user home directory, and then that's going to be stored here. And then they're going to use that home directory as the first part of this string, which will then be passed into this path file path.join, which will then join these two together. And then it creates that target file path for the BattleNet. All right, so just a quick video on Go strings. It's not very pretty to look at in any of these tools, but I believe there's some plugins to help with this. I haven't really used a lot of them. Should probably check that out more. But once you know how to actually look at them, you can use some quick functions like bb.read to look at the actual Go string. Cool.